Hello, everyone, again. These are the other two problems, which are the 1D motion problems for the practice questions for quiz 1. Um, so I like this style of question for number 3. This is the cat leaping upwards. In the very beginning of the course, it's important to learn some stuff that you may not have done in other classes, all right? You want to organize information. You want to do things like draw a picture. All right, so I want you to be able to draw what's going on here. All right, now you should also read the rest of the questions. All right, is that there's a part A, B, C, D, E, and F, and you want to think about what's going on in there. Right? Is that we make some questions like in part D, what's the maximum height? And I tell you explicitly, it's not the number you're given. So you have to do some calculation. Right? You're going to have to figure out what that is. I'd also say re-examine what you know. So you're going to have to basically edit your drawing a little bit or make a new drawing. Right? Now this is all condensed so that you have the questions all on a piece of paper, and you can write on this. When you get it on the test, you'll have some space for each section, and you can use extra paper. Right? So you don't have to do it necessarily exactly like I do it, but you want to have all the important bits in it. Right? So for number 3, we're going to have a cat. I'm just going to draw the cat like this. Right? I'm doing a very Mr. Brown cat here. Right? It's going to leap up in the air. It got startled. It goes, ah! And goes, and it gets to here. This is from the ground, so this is y equals 0. This will be 0.875. And this will be t equals 0. And this will be, what is it, 0.220 seconds. Right. So I also want you to remember, if you throw an object up in the air, or if you see something jump up in the air like this, once it's in the air, it typically slows down and then falls back down to the ground. You cannot calculate velocities based on just this number and this time. This is an object that's accelerating. Right? But this is enough for our drawing. Right? This is our drawing. This is what we know. Right? Is that it goes to these places. What we don't know, right? This involves maybe let's make a table, right? We could do delta y. Right now it's 0.875 meters. V initial y, we don't know. V final y, we don't know. It's not 0, because in part D, when we get to the maximum height, that's where it will be 0. Our acceleration is not known yet, but we can make an assumption about it. And our time will be 0.220 seconds. But we can talk about this acceleration, right? We're also saying up is our positive y direction. Gravity is always downwards. Right? So this is going to be negative, and it's always going to be 9.8 meters per second squared. Right? So that's part A is drawing the picture, trying to figure out what stuff is known and unknown, right? This is what this is. Part B is coming up with a plan. If this is what we have, what can we do? Right? So we go over here, right? I'm going to label this is part A. And I'm going to be careful and label, right? This is because it's free fall. And then these are our knowns. Right. And you don't have to do it exactly this way, but I should see this information. I should see that the acceleration's minus 9.8. I should see delta y and t here. Right? I should see those things as part of your organization. Right? So if this is our information, we want the initial velocity. And we want to think about it for a minute. And be like, well, what equation would have the things that we do have, and it doesn't have v final. We don't want that. And we can solve what we need out of it. And so for part B, if we're trying to come up with an equation, I would say we want to find the initial given these other things. We want to do delta y is going to be v initial y times t plus 1/2 ay t squared. Right? That's what we want to do. And we're going to solve for v initial. So we could organize this a little further, but this is the thing we actually want. This is our part B. All right. This is what I'm looking for, is can you pick the equation based on what you know and don't know. All right, so I'm judging this based on what you tell me up here. All right, if you think that you know the v initial, then I'll say, oh, well, if you know the v initial, well, why are you trying to find it? But if I know the v final, then it makes sense to do something with that. All right, so I'm being careful here. If I know something, I'm not judging part B based on, well, what equation did I expect to use? I'm judging it based on what did you do. All right. So, but anyway, that's our part B. Once we have that, then we can just start doing some algebra. All right. So for part C, that initial velocity, well, we need to get this term by itself. And that's going to be delta y minus 1/2 ay t squared. And then we'll divide by the time. And this one and that one will cancel out. Right. And so we'll have our v initial is going to be our delta y over t. That's 0.875 meters over 0.220 seconds. And you'll note that's your average velocity. That's the distance over the time. But in the beginning, you go faster. At the end, you're slowing down. You're going slower. This is just what it is somewhere in the middle. All right, so there's a correction. Plus 1/2 minus 9.8 meters per second squared. And here we just have 1t, so 0.220 seconds. Right. And that will get us our v initial. Right. So we put that in the calculator. Right. Here's our calculator. I'm zoomed in a lot. Hopefully it's not too terrible. All right. 0.875 divided by 0.220. Get a preliminary number, and then we add 0.5 is the 1/2 times 9.8, and make sure we get the negative there. 9.8 times, and then we'll have 0.220. Oh, we're subtracting it here. So it's minus a negative. You have to be very careful about these minus signs. All right. So this minus sign is coming from this algebra. This minus sign is coming from G pointing downwards. So they will cancel out, and you'll get an overall plus. And so we calculate, and we get a V initial is going to be 5.06 meters per second. We check that term has units of meters per second. This term, the seconds cancel, that has meters per second. So it works. It's velocity, everything's good. Right. So that's our part C. So now part D is a different motion. It's not the same. All right, so I'm going to draw a line here. Let's get this over so we have an image. So for part D, all right, we're going to go from the ground. So here's our cat that's jumping. 5.06 meters per second. It's going to get up here. At that maximum height, 0.875 was down here. The cat kept going upwards. If you want to trust, if you don't trust that, calculate what V final is. Right? We have a spot for V final. We can calculate what that is. It's still positive. Right? This is going to be about 2 meters per second change, and so it goes from 5 down to about 3. But still positive here, still going upwards. At this point, this is where it returns back to the ground. This is going to be V in the y direction is 0 at that point. Right. So what we know here is delta y is our goal. V initial is a known, 5.06 meters per second. V final is 0 because it's max height. Our acceleration is minus 9.8 meters per second squared because it's free fall. And our time, we don't know how much the time is. And so that's our drawing, that's our assumptions. We want to say, well, what equation could we use that doesn't use the time and will use these other things? How are these 4 things related but not the time? And we have an equation for that. It's going to be V final squared is V initial squared plus 2a delta y. So we can calculate based on that. So let me get our paper here. So this is part D again. We know V final is 0. V initial is this 5.06 meters per second squared plus 2 times minus 9.8 and we will have a delta y here. Right. So this term's positive, it has to equal 0. This term needs to be negative. We have a negative here. We just do some algebra. Delta y should be, we want to get this on the other side, so minus 5.06 meters per second squared. And then we want to divide by these 2 terms. 2 times minus 9.8 meters per second squared. And so when we do the units, we have to square these units, and then we get rid of those units. We're left with a distance. We're left with meters. And we have to do some math. And when I put that into the calculator, I'm going to get that this delta y should be plus 1.30 meters. Cats can jump 1.30 meters. I'm okay with that. Right. So we just want to be careful as we're doing this part D. We'll make sure, kind of pay attention to what things do you know, what can you assume. Don't reuse numbers that numbers from part A are about this other point. that's not what's going on, right? And you're not going to get this problem. You're going to get a problem like that. But, you know, whatever that problem is, it's going to have a certain, you know, you need to write your information out. You need to draw your picture. You need to write your algebra out so I can see what you did. Right? Don't skip so many steps that I have no clue what you did. That's the important bit. All right. Part E. There's an average velocity. Remember I said what this average velocity was up here? I said, hey, this is the average velocity and this is a correction term. All right. So we can find that. The definition of average velocity is that it is the total distance covered over the time. And I try very much to give for you problems you don't have to make a, you don't have to have solved part C to solve part E, right? All we need out of this is the numbers we started with in the problem. During the motion up to 0.875 meters, right? What is this number? It's going to be 0.875 meters over 0.220 seconds, and 0.875 divided by 0.220 is going to be 3.97 meters per second, and you can't see that. 3.98 meters per second. Total distance covered over some segment divided by total time. Right. Now, if you misread that and you found up to the max height, you'd have to find when is this? When is it at the max height? But you could do that, and you could do this average over this, and you could figure out what that is. That's not too terrible. And if you did that, you'd get most of the credit because you showed you know the skill. It's just that you misread the problem. There's nothing wrong with that. Right? But you have to show that you know that particular skill. You can't misread it so badly that you start doing calculus or something. Right? So finally, part F, right, is what is the acceleration? Like, well, how do I calculate the acceleration? Well, you don't. You've been assuming it all the way around. Everywhere in the problem, we said the acceleration was minus 9.8. We said it was that here. We assumed that. If you really want to be thorough, you'd go through and you'd check and be like, well, do I get other answers that make that a consistent thing? No, this is free fall. You can just say the acceleration here is minus 9.8. That's perfectly fine. Nothing wrong with that. So sometimes I give you a question, and if it's not worth a ton of points, then it may just be free points. I may just be like, hey, do you know this? That's fine. There's just answer it, and yeah, you know it. Good. And sometimes I need to check, do you know to assume free fall? Or do you know what the velocity is when you're at the maximum height? Right? Those are useful things to know. Alright, so we need to do the fourth problem. This is one of these segmented motion problems. Right? Now the reason for doing a segmented motion problem is that we want to, there we go. Okay. So we want to have a couple of parts of the problem. We want to try work with different bits of these equations. Right. We have a train It's going in 3 segments. If you're okay with this, I'm just going to rely on the drawing that we have, that you've already made. Right? I'm not going to try to draw a train. The motion's going to be in 3 segments. Right? From between A and B, we don't know what that distance is. Right? So what I would do is sort of keep up with 3 different chunks of info. I'd have from A to B. Right? All right. So I'd have delta x is something we don't know. V initial, well, if you start out, you leave from rest, that's 0. V final, we don't know. Maybe that's something we need to know. Right? Our acceleration, we do know. That's in the problem. A is 1.27 meters per second squared. And our time during this chunk is 16 seconds. Right. So out of this information, we could get some stuff. The second part is from B to C. What do we know during that? We know it's constant speed. We know it takes 3 minutes to do that. So constant speed means the acceleration is 0. We don't know the velocities yet. So we don't know delta x. We know V initial is whatever we get for V final. And we know V final is going to be V initial. Our acceleration is 0. That's how we know this stuff's true. And our time is 3 minutes, which equals 180 seconds. All right, you'd convert 60 seconds in a minute, so 60 times 3. Right. And so the third part is to go from C to D. And for C to D, we know the distance. Delta x is 1 kilometer, so 1,000 meters. Right. We know V initial will carry over, but we don't know what it is yet. We're going to have to calculate what it is. V final, we do know. It has to come to a stop at the station. Our acceleration is something we don't know. That's a goal. And in our time, we don't know. All right. So once we get, right, we have 2 things here. Once we get V initial, we would have a third. That comes from here. We have 2 things here. Once we get V initial, we'd have enough to get the distance. That comes from here. And so over here we have 3 things. It makes sense to start filling in the table from A to B. Right. So we want to know what this V final is, and we want to know what delta x is. So V final is probably the easier one, right? We're trying to relate a velocity to the initial velocity acceleration time. That is V final is V initial plus AT. And then V initial is 0. And so this will be 1.27 meters per second squared times 16 seconds is V final. And so if you calculate that, 1.27 times 16, we will get 20.32 meters per second. So V final is, realize that's right at the edge of the paper, 20.32. So that goes up here. We know that this is 20.32 meters per second, and that means so is this, and that means so is this. Right. So now we can fill in these other things. Right. But we do also need this delta x here, right? Because if we look at what it's saying, how long does it take? What's the time? How far apart are they? And then what is this acceleration over here finally. Right? So we needed this as a preliminary to do all these other things. Right? So part A. All right, part A in the questions. How long does the trip take? Well, we need the total time. We need this one. Right? So we're looking for this time. We have these numbers. We have an initial and a final velocity and a distance. We have a relationship. We don't know the acceleration. We don't need it. We can do the average velocity equation. Delta x is v final plus v initial all over 2. That's our average velocity times our time. Right? And we're solving for the time. So the time, multiply both sides by 2, divide both sides by the parentheses, we'll get 2 delta x over v final plus v initial. All right, so some algebra will get us, multiply both sides by 2, divide by v final plus v initial. And we need to put in some numbers. We'll have 2 times 1,000 meters, and we'll divide by, well, v final is 0 plus 20.32 meters per second. So we go and we plug this stuff into our calculator. I get this time should be 98.4 seconds. Right. So now the total time is going to be 16 seconds plus 180 seconds plus 98.4 seconds. And so we add plus 180 plus 16. I get delta t is 294 seconds, which is almost 5 minutes. 5 minutes is 300 seconds. Right? If we divide by 60, it'll be 4.91 minutes. So this is our answer for part A. Hooray! Now for part B, we want to know what the stations are. And the stations, we need to know this distance and this distance. Right. Well, now that we have a time and a velocity, we can get this. Now that we have this information, we can get this. Right. Oops. Right. Right. So that's our part B. So that's what we're looking for. So new sheet of paper. All right. So hopefully you're following along. If I realize I'm kind of stuck here trying to calculate some of this stuff where I don't have quite the space to do it. But now we're working with these numbers. Right? So from A to B, we want to find that distance given v initial, acceleration time, v final. We can use the average velocity formula again. There's nothing wrong with that. We can use the equation of motion. Delta x is v initial t plus 1/2 at squared. We can use anything that has delta x in it because we know 4 of the 5 things. I'm going to do the average velocity first. All right. V final plus V initial over 2 times the time is going to be 0 plus 20.32 meters per second over 2 times 16 seconds. Right. And so this should give us 20.32 divided by 2 times 16 163 meters. That's part of our answer. And if you want to check, does that make sense? Well, you can try it a different way. Right? And I'm doing it a different way because there's more than one way to solve this problem. So if I did delta x is v initial t plus 1/2 at squared. This term is 0. And so we'll have delta x is 1/2, our 1.27 meters per second squared times 16 seconds squared. We put that in the calculator. 0.5 times 1.27 times 16 squared. We'll get, again, 163 meters. So there's one other way I can think of, and that's to use v squared as v initial squared plus 2ax. And that should get us the same number for a to b. All right. So now we need to do b to c. B to c, that's constant velocity. So we can just do our grade school distance is velocity times time. Delta x is v in the x direction, delta t. This is 20.32 meters per second times 180 seconds. And so delta x will be 20.32 times 180. That is, well, I get 3,657.6. 3 sig figs. This is going to be, well, keep 4 sig figs. 3,658 meters. So now we can do the total, right? All three segments. Right. Delta x will be from A to B is 163 meters. From B to C is 3,658 meters. And from C to D, that's given in the problem, is 1,000 meters. So delta x will be, we add 163 and we add 1,000. Now we think about sig figs, 4,820 meters. All right, I get a 0.6 that I don't care about. It rounds to 4,820 meters. That's 4.8 kilometers. Does that make sense for trains? That's 3 miles. So in a city, yeah, that makes some sense. I don't know if these numbers are reasonable otherwise, but that's a distance that's not like unbelievable. All right. So part A and part B, right? We've done that. Part C is this little bit of acceleration. So let me get a corner of this. All right. This is the info for B. So for part C, all right, we need that acceleration given the numbers that we have before, right, from C to D. So these are our numbers. We can do, well, we have the time, right? Now we have the time when we did part A. If you remember, we did this part A, we got 98.4 seconds. So we can use that if we want to. We don't know that that's necessarily correct when we're trying to do the test, right? So we should try to use things that we don't already know. Sorry, that we've been given in the problem. We know that these numbers in the problem are correct. So I would go and say, well, I don't trust the time using those 4 things. V final squared equals V initial squared plus 2a delta x. And I would solve for a. You might remember doing this in the math review if you did the math review. V final squared minus V initial squared over 2 delta x. And we can put numbers in. V final is 0 minus. Be careful with this minus sign. When you square stuff, you should get a positive number out of it. So we'll have 20.32 meters per second squared. That's going to be positive. It's about 400. But that minus sign has to persist. Right? It's not in the square. It's outside of it. And the reason for that will be apparent in a minute. 2 times 1,000 meters. Right. So units will cancel there. This is like 413. We divide by 2,000. I get A is minus 2.06, sorry, 0.206. Let me cross that out. Minus 0.206. There's some other terms. Meters per second squared. So now I'll draw the train briefly. Right. This is how far it goes. It goes to 4820 meters. And in this last little segment, its acceleration is that way. Right. And its velocity is 20.32 meters per second. All right. So when I sketch that out, when you sketch it out for a second, it becomes apparent. The train's got to slow down. Slowing down means opposite directions. So if it goes to the right with a positive velocity, then it has to have a negative acceleration to slow down. And that's what this number is. So that's a lot. I mean, I've been talking here. That segment for that problem is 20 minutes, 25 minutes. That's a lot. If I give you a problem like this, it probably would be simpler. This was an old test problem that I gave back when I tended to give students a lab period. I had 2 hours to do 4 or 5 problems. Right. And I've pulled this and a few other problems from old tests. And I've made some new problems up. All right, so the practice problems you're getting are things that I thought would be reasonable on a test. If you went and took this class at Radford or at Tech, you'd probably get similar problems. So I've been yammering 38 minutes. I'm going to scan these, upload them. You're going to get the video uploaded. Hopefully you've seen a big chunk of 1D motion and a big chunk of vector math, of just practice problems. If you have questions, email. All right, we can talk about this. Come see me tomorrow. Is Thursday in lab. If you're watching this, it's August 27th when I'm recording. So come see me on Thursday the 28th. Otherwise, all right, if you're in university physics, your quiz is on Friday. If you are in one of the other classes, then it's going to be a little bit later next week. All right. I guess that's about it.